Introduction to AI and Machine Learning. 1.1 Defining AI and Machine Learning. Artificial intelligence, AI, is an expansive field of computer science that emphasizes the development of systems capable of performing tasks typically requiring human intelligence. These tasks include learning from experience, reasoning to reach conclusions, understanding natural language, and recognizing patterns in data. AI aims to simulate cognitive functions, such as perception and decision-making, with an overarching goal of creating machines that can think and act independently. Its origins can be traced back several decades, with contributions from a multitude of disciplines including mathematics, psychology, and neuroscience. Machine learning, ML, is a subset of AI focusing on the ability of machines to automatically learn from and adapt to new data without being explicitly programmed. ML algorithms use historical data as input to predict new output values, recommendations, or decisions. The learning process involves building a mathematical model based on sample data, known as training data, which the machine uses to make predictions or decisions without being directly programmed to perform the task. Machine learning's roots are in early AI history, but it has risen to prominence alongside the digital age due to the exponential increase in both computational power and data availability. In explaining the distinction between AI and ML, it is important to clarify that all machine learning is AI, but not all AI incorporates machine learning. AI includes the broader concept of machines being able to carry out tasks intelligently, whereas machine learning is specifically concerned with algorithms that allow computers to learn from and make predictions on data. Other domains within AI, such as expert systems in robotics, may not involve learning from data, but they are considered a part of AI because they exhibit some form of human-like intelligence. The development of AI and ML has led to the creation of another related field known as deep learning, DL. Deep learning is a subset of machine learning that uses layered neural networks to simulate the human brain's processing of data. These neural networks are designed to recognize patterns by filtering inputs through layers in which each layer defines specific features based on the previous layer's output. Deep learning models become more accurate as they process more data, leading to significant breakthroughs in areas like computer vision and natural language processing. Implementing AI and ML systems necessitates meticulous data curation. The quality and quantity of data fed into AI and ML models are critical in determining their performance. Data engineers and scientists spend substantial time pre-processing data, handling missing values, and structuring it in a way that is feasible for the model to interpret. The data undergoes cleaning, normalization, transformation, and feature extraction before being suitable for training AI models. As AI and ML models are trained, they undergo various validation and testing processes to ensure that their predictions are accurate and generalizable. These phases are crucial to prevent phenomena like overfitting or underfitting, which compromise the model's performance on unknown data. Overfitting occurs when a model is too complex and tailored to the training data, failing to generalize to other datasets. Underfitting happens when the model is too simple to capture the underlying pattern in the data. A balance must be found to create a robust and predictive model. The field of AI and ML also places significant importance on the ethics of algorithmic decision-making. As these systems increasingly influence sectors like finance, healthcare, and law enforcement, the potential for biases embedded within AI algorithms is a serious concern. Ethical AI involves ensuring that AI respects human rights and values and is fair, transparent, and accountable. This includes confronting issues of data privacy, surveillance, and the potential for AI to perpetuate existing societal biases. The practical applications of AI and ML are vast and affect nearly every aspect of modern life. In healthcare, AI systems assist in diagnosing diseases, predicting patient outcomes, and personalizing treatment plans. In finance, machine learning algorithms help detect fraudulent transactions and automate trading strategies. In transportation, AI enables self-driving cars and intelligent traffic management systems. These are just a few examples of the myriad ways AI and ML technologies are reshaping industries. The research in AI and ML is continually evolving, with state-of-the-art techniques being developed at an accelerating pace. Advancements in computing hardware, such as the development of graphics processing units, GPUs, and tensor processing units, TPUs, have been instrumental in advancing AI research. These specialized processors can perform the complex mathematical operations required for ML at an unprecedented speed and scale, facilitating more advanced and efficient AI models. In the academic and commercial sectors, the study of AI and ML continues to expand, with a push towards developing more efficient algorithms that require less computational power and data, while also enhancing the interpretability and explainability of the models. As the field matures, the ongoing research addresses not only the technical challenges, but also the societal implications of automated systems. With these advancements, AI and ML are poised to remain at the forefront of technological innovation and continue to influence the evolution of society. 1.2 History and Evolution of AI. Artificial intelligence, AI, is a field of computer science that focuses on the creation of machines capable of intelligent behaviors that are traditionally associated with human thought. The roots of AI can be traced back to antiquity, with the concepts of automatons and artificial beings found in mythology and early philosophical texts. Nevertheless, the formal foundation of the discipline as a scientific endeavor began much later. The 20th century brought notable advancements in mathematics and formal reasoning, which paved the way for modern AI. Alan Turing, a British mathematician, was among the pioneers who addressed the question of machine intelligence with his seminal paper, Computing Machinery and Intelligence, in 1950, which introduced the Turing test as a criterion for machine intelligence. AI continued to evolve from its conceptual beginnings. In the 1950s, the term artificial intelligence was first coined by John McCarthy, an American computer scientist widely regarded as one of the founders of the field. McCarthy organized the famous Dartmouth Conference in 1956, which brought together researchers interested in neural networks, the study of automata, and complex information processing. This conference is often considered the birth of AI as a formal academic discipline. During this period, researchers were optimistic about the prospects of creating machines that could simulate all aspects of human intelligence within a generation. Despite initial enthusiasm, AI soon encountered its first significant setback. The early decades of AI research were marked by the development of simple algorithms and rule-based systems that struggled to scale up or deal with uncertainty. These systems, while effective in structured environments, failed to perform well in more complex real-world scenarios. This led to a period known as the AI winter in the 1970s and again in the late 1980s, where funding and interest in AI research waned due to unmet expectations and technical limitations. However, the AI winters were followed by periods of resurgence. The 1980s witnessed the rise of machine learning, a subset of AI centered around the idea that machines could learn from data, recognize patterns, and make decisions with minimal human intervention. The introduction of algorithms such as backpropagation for neural networks enabled computers to train themselves to perform tasks by being fed large amounts of data. This marked a shift from handcrafted rule-based systems to data-driven learning models. Advances in hardware, particularly the development of faster processors and increased data storage, further facilitated this shift. The 1990s brought further progress with the expansion of the Internet and the exponential increase in digital data. Researchers began developing more sophisticated machine learning algorithms, and AI applications started to become more prevalent. Support vector machines, decision trees, and ensemble methods like random forests improved the performance of AI systems in classification and prediction tasks. This decade also saw AI's increasing impact on industry, with the adoption of automation and robotics for repetitive tasks. In the early 2000s, AI benefited from the confluence of several factors. The availability of big data, advances in algorithmic complexity, and significant improvements in computational power, especially with graphics processing units, GPUs, led to an explosion of AI capabilities. This period saw the development of deep learning, a powerful subset of machine learning involving deep neural networks with many layers. These advances made it possible for machines to perform highly complex tasks such as image recognition, natural language processing, and strategic game playing at or above human-level performance. A landmark moment in the history of AI was in 2011, when IBM's Watson defeated human champions in the game show Jeopardy!, highlighting the progress of natural language processing and understanding. This was followed in 2016 by Google DeepMind's AlphaGo, an AI program that defeated a world champion Go player, a feat previously thought to be decades away. These events publicized AI's potential and transformed public perception of the technology, leading to a surge in investment, research, and development of AI applications across various industries. The present state of AI is characterized by widespread adoption and an emphasis on developing ethical and responsible AI. Researchers are focusing not just on making AI more capable, but also on understanding its decision-making processes and ensuring it is fair and unbiased. This includes exploring explainable AI, which seeks to make AI decisions transparent and comprehensible to humans. Furthermore, AI research has branched out into new directions. Reinforcement learning, a paradigm where AI learns by interacting with an environment and receiving feedback, has been used to train agents in complex environments such as video games and robotic control. The integration of AI with other disciplines, such as neuroscience and cognitive science, is leading to richer models of human and machine intelligence. Looking ahead, the future of AI promises further integration with other technologies such as the Internet of Things, IoT, blockchain, and quantum computing. The combined potential of these technologies with AI could lead to transformative changes in society. However, alongside the promise, there are also challenges. Managing the societal impact of automation, addressing privacy and security concerns, and ensuring ethical use of AI are some of the critical issues that need to be addressed as AI continues to evolve. The history and evolution of AI reflect a journey of aspiration, challenging setbacks, and remarkable breakthroughs. As AI becomes more sophisticated, it continues to push the boundaries of what machines are capable of, shaping the way humans interact with technology and influencing the future trajectory of society. The continued evolution of AI requires a concerted effort from researchers, practitioners, policymakers, and the public to steer its development toward beneficial outcomes for all. 1.3 Key Concepts in Terminology. Artificial intelligence, AI, is a field of computer science that aims to mimic or recreate human intelligence in machines. It is a broad umbrella term encompassing various technologies and approaches that allow computers to perform tasks that typically require human intelligence. These tasks can range from recognizing speech and images to making decisions and understanding natural language. AI systems improve through experience, employing algorithms to analyze data and draw conclusions or insights without explicit programming for each individual task. Machine learning, ML, a subset of AI, is a method of data analysis that automates the building of analytical models. It involves teaching computers to learn from data and make decisions or predictions based on that data. The essential premise of machine learning is that it allows machines to adapt to new scenarios independently by generalizing from previous experiences. This is achieved through the use of algorithms that discover patterns and generate insights from the data they are fed, potentially improving their performance over time as they process more data. Algorithms, the backbone of machine learning, are sets of rules or instructions given to an AI system to help it learn from data. They range from simple formulas to complex mathematical models. An algorithm in an AI context is akin to a recipe for a chef. It provides a series of steps to achieve a specific outcome. Different types of algorithms are suited for different types of tasks and data sets, and the choice of algorithm can significantly affect the performance of a machine learning model. Data is the fuel for machine learning algorithms. High-quality, relevant data is crucial for training effective AI models. Data can come in various forms: structured data such as databases and spreadsheets, and unstructured data such as text, images, audio, and video. The quality and quantity of the data being used directly impact the performance and accuracy of the AI system. In the areas of AI and machine learning, practitioners often spend a considerable amount of time pre-processing and cleaning data to ensure that it is fit for use in model training. Training a machine learning model involves providing an algorithm with data and allowing it to learn and make inferences. During the training phase, the model attempts to find patterns or understand the structure of the data. For instance, this stage could involve a predictive model learning from a historical dataset to forecast future trends or behaviors. The model's efficacy at this stage is often evaluated through a process called validation, using a subset of the available data that has been set aside for this purpose. Supervised learning is a common type of machine learning where the algorithm is trained on a labeled dataset. In this context, labeled means that the input data is paired with the correct output. The machine learning model uses this training data to learn the relationship between the input and the output. Once trained, the model can apply this learned relationship to new unseen data to predict or categorize outcomes. Supervised learning is commonly used in applications where historical data predicts outcomes, such as credit scoring and disease diagnosis. On the other hand, unsupervised learning involves training an algorithm on data that does not have explicit labels. The goal of unsupervised learning is to model the underlying structure or distribution in the data in order to learn more about the data itself. Techniques in unsupervised learning, such as clustering and dimensionality reduction, can identify natural groupings among data points or reduce the number of variables under consideration. Semi-supervised learning is a hybrid approach that uses a small amount of labeled data and a larger amount of unlabeled data to train a model. This approach is particularly useful when labeling data can be costly or time-consuming. Semi-supervised learning algorithms leverage the small amount of labeled data to guide the learning process with the unlabeled data, and have become more prevalent as businesses seek to harness the value of vast amounts of collected but unlabeled data. Reinforcement learning is different from supervised and unsupervised learning. It is an area of machine learning concerned with how intelligent agents ought to take actions in an environment in order to maximize the cumulative reward. This type of learning is inspired by behaviorist psychology and involves learning to make decisions by taking actions and being rewarded or penalized. It is used in various domains, such as in the development of autonomous vehicles, where the system receives feedback in the form of rewards or punishments as it navigates its environment. Neural networks form the basis of deep learning, which is a sophisticated subset of machine learning. Neural networks are designed to imitate the functioning of the human brain, enabling the machine to recognize patterns and characteristics in large amounts of data. These networks are composed of nodes or neurons organized in layers. Data inputs are processed through these layers, with each neuron assigning a weighting to its input, which is then adjusted through the learning process. Deep learning is particularly useful when dealing with large and complex datasets, such as those found in image and speech recognition. Understanding these key concepts is crucial for anyone looking to delve into the field of AI and machine learning. The terms and methodologies discussed form the bedrock upon which more advanced AI strategies are built. As technology rapidly evolves, these concepts continue to gain prominence and utility across a multitude of industries. While the technicalities of AI and machine learning may be intricate, a clear grasp of the basics creates a strong foundation for further exploration and application. 1.4 Types of AI: Narrow AI versus General AI. Artificial intelligence, AI, can be broadly categorized into two main types: narrow AI and general AI. Narrow AI, also known as weak AI, refers to artificial intelligence systems that are designed and trained for a specific task. These systems operate under a limited predefined range or set of functions. Narrow AI is prevalent in our daily lives, often without us realizing it. Examples of narrow AI include voice assistants like Alexa and Siri, recommendation systems on e-commerce sites, and even the spam filters in email services. Narrow AI systems are very effective at handling routine, repetitive tasks and can often outperform humans in speed and accuracy for those specific functions. In contrast, general AI, also referred to as strong AI or artificial general intelligence, AGI, is the type of artificial intelligence that is envisaged to have the ability to understand, learn, and apply knowledge in a way that is indistinguishable from human intelligence. General AI would have the capacity to solve a wide range of problems and carry out tasks in various fields without being limited to a particular subset. Although the idea of general AI is compelling and has been a subject of science fiction for decades, as of my knowledge cutoff in 2023, it remains a largely theoretical concept. Currently, no such systems exist that can display the adaptive, versatile intelligence of human-like general AI. The development of narrow AI is driven by the use of specialized algorithms designed to perform singular tasks. Machine learning, ML, a subset of AI, enables these systems to improve their performance over time based on data without being explicitly programmed. Narrow AI systems use a combination of methods, including pattern recognition, natural language processing, and other specialized algorithms, to perform their designated tasks. The field of machine learning includes various approaches, such as supervised learning, unsupervised learning, and reinforcement learning, each used to tackle specific kinds of problems targeted by narrow AI. The pursuit of general AI involves creating systems that possess general cognitive capabilities that enable them to learn from experience, reason, and use knowledge in unfamiliar situations. While machine learning plays a crucial role in both narrow and general AI, the approach for general AI is significantly more complex as it aims to create a flexible and transferable intelligence. General AI requires not only machine learning algorithms, but also a framework that supports the integration of different types of learning and knowledge representation to simulate human-like thought processes. The distinction between narrow AI and general AI is significant because it affects how AI is applied in various sectors. Narrow AI systems are currently the backbone of numerous industries, facilitating automation and enhancing decision-making through data analysis. They are deployed in finance for fraud detection, in healthcare for diagnostic aids, in manufacturing for quality control, and many other sectors. These systems are designed to execute well-defined repetitive tasks at scale, making them extremely valuable for efficiency and productivity. Conversely, the potential use cases of general AI are much broader and more profound. General AI promises to revolutionize technology by creating systems that can perform any intellectual task a human can do. It would lead to advances across all domains, including complex problem-solving in domains like scientific research, versatile physical tasks in robotic applications, and sophisticated decision-making in business and government. However, the realization of general AI remains a long-term goal, and with it comes an assortment of ethical and existential concerns about the interaction and coexistence of humans and intelligent systems. The ethical implications of narrow AI are more immediate and practical. Although narrow AI systems are not sentient or conscious, they still raise important questions about privacy, accountability, and bias. As these systems often operate on vast amounts of personal data, ensuring data protection and privacy becomes crucial. Additionally, as AI systems make or assist in making decisions, the clarity about who is responsible if those decisions lead to unintended consequences is imperative. Bias in AI systems, stemming from biased data or algorithms, is another challenge, potentially leading to unfair outcomes in areas like job recruitment, loan approvals, and law enforcement. The term narrow AI can be somewhat misleading because within its scope, AI can perform tasks with a level of complexity and sophistication that may seem broad. However, it is called narrow because each system is confined to a particular task or set of tasks. A facial recognition system might be incredibly advanced, able to analyze and identify millions of faces, but it does not have the capability to understand language or manage a supply chain. Its intelligence, therefore, is considered narrow. In the development of AI, there exists a continuum of capabilities between narrow AI and the theoretical general AI. Some AI systems are beginning to showcase a broader range of abilities within certain domains, indicating progressive strides towards more general capabilities. However, these systems are still categorized as narrow AI since they do not possess the flexible general-purpose problem-solving abilities ascribed to general AI. This progression illustrates the dynamic and evolving nature of AI research, as systems are continuously improved and their capabilities expand, moving the field incrementally towards the more sophisticated end of the spectrum. Overall, the types of AI, namely narrow AI and general AI, represent fundamental concepts at the core of AI research and development. Understanding the distinction between these types of AI is essential for grasping how artificial intelligence fits into our world today and how it might evolve in the future. The investigation into general AI continues to push the boundaries of what is possible, prompting ongoing discussions about the societal transformations that might accompany such advancements. Meanwhile, narrow AI innovations maintain a significant and growing impact on various aspects of daily life, industry, and commerce, demonstrating the transformative power of AI even within its current limitations. 1.5 Overview of Machine Learning. Machine learning, ML, is a subset of artificial intelligence, AI, focused on building systems that can learn from data, identify patterns, and make decisions with minimal human intervention. The concept of ML is based on the idea that machines can be given access to data and the ability to learn for themselves. It has evolved from pattern recognition and computational learning theory in AI and is now used extensively in a variety of fields. ML algorithms are used in applications such as email filtering, speech recognition, and computer vision, where it is difficult or infeasible to develop conventional algorithms to perform the needed tasks. A primary goal of machine learning is to enable computers to learn automatically without human assistance or intervention and adjust actions accordingly. This is achieved by developing algorithms that can receive input data and use statistical analysis to predict an output while updating outputs as new data becomes available. These algorithms are often categorized as supervised, unsupervised, or reinforcement learning, each with different approaches and uses. Supervised learning algorithms build a mathematical model on a set of data that contains both the inputs and the desired outputs. Unsupervised learning algorithms, on the other hand, work on data that does not have labeled responses and are left to find structure in its input data. Supervised learning involves training a model on a labeled dataset, which means that each training example is paired with an output label. This form of learning is analogous to a teacher guiding the learning process, where the model learns from the training data and makes predictions or decisions based on that data. Common supervised learning algorithms include linear regression for continuous output values, logistic regression for binary outcomes, and complex neural networks for various tasks such as image and speech recognition. The model's performance is evaluated using unseen data called the validation set, and the ultimate aim is to minimize errors to improve accuracy. Unsupervised learning, in contrast to supervised learning, deals with input data without labeled responses. The system attempts to learn the patterns and the structure from the data without explicit instructions on what to predict. Clustering and association are two common types of unsupervised learning. Clustering algorithms, such as k-means clustering and hierarchical clustering, are used to group a set of objects in such a way that objects in the same group or cluster are more similar to each other than to those in other groups. Association rule learning algorithms, such as a priori and éclat, are used for discovering interesting relations between variables in large databases. Reinforcement learning is somewhat different from supervised and unsupervised learning. It is concerned with how software agents ought to take actions in an environment to maximize some notion of cumulative reward. Reinforcement learning involves learning what to do, how to map situations to actions, so as to maximize a numerical reward signal. The learner is not told which actions to take, but but instead must discover which actions yield the most reward by trying them. This type of learning has a strong connection to decision-making under uncertainty and has been applied to various areas, including game playing, robotics, and autonomous vehicles. The process of a machine learning project involves several key steps: data collection, data preparation, model selection, training, evaluation, and deployment. Data collection involves gathering the raw data that the algorithms will learn from. Data preparation, which often takes the bulk of a data scientist's time, includes cleaning the data and transforming it into a format that the algorithms can work with. Model selection involves choosing the appropriate algorithm based on the problem at hand and the nature of the data. Training the model involves feeding it the data and allowing it to learn. Evaluation means testing the model's predictions using a separate dataset to see how well it performs. Finally, deployment is putting the trained model into production where it can start providing insights or automating tasks. Machine learning models can be evaluated using various metrics. In classification tasks, common metrics include accuracy, precision, recall, and the Ch.1 score. In regression tasks, metrics such as mean absolute error, mean squared error, and R-squared are used. These metrics provide information on different aspects of a model's performance. For instance, while accuracy measures the percentage of correct predictions, precision and recall focus on the model's performance in predicting positive cases. Choosing the right metric is important as it guides the model's fine-tuning and can significantly impact the performance of the machine learning system in real-world applications. One of the challenges in machine learning is overfitting, where a model learns the detail and noise in the training data to the extent that it negatively impacts the performance of the model on new data. This means that the noises or random fluctuations in the training data are picked up and learned as concepts by the model. The opposite of overfitting is underfitting, where a model is too simple to capture the underlying structure of the data. There are several techniques to combat overfitting, such as cross-validation, where the data is divided into parts and the model is trained on some segments and validated on others, regularization techniques that penalize complexity, and pruning decision trees. The field of machine learning is constantly evolving with emerging subfields such as deep learning, which involves neural networks with many layers that enable learning of data representations in increasing levels of abstraction. Another subfield is transfer learning, where a model developed for a specific task is reused as the starting point for a model on a second task. This versatility and adaptability make machine learning a powerful tool in modern technology. Its applications are numerous, from healthcare to finance to transportation, and its potential is still largely untapped. The future of machine learning is intertwined with the advancement of computing power, data availability, and algorithmic innovations. As hardware becomes more capable, datasets more comprehensive, and algorithms more sophisticated, the scope of what machine learning can achieve is expanding. The ethical considerations of machine learning are also coming to the fore as it becomes ubiquitous in society. Issues such as privacy, transparency, and bias must be conscientiously addressed to ensure machine learning benefits everyone and minimizes harm. As the field grows, the commitment to ethical practice will be as important as the technology itself. 1.6 AI in Society: Impacts and Ethical Considerations. As artificial intelligence, AI, and machine learning become more integrated into society, the impacts of these technologies extend beyond their technical capabilities to affect nearly every facet of human life. From influencing decision-making processes in business and governance to altering labor markets and provoking philosophical debates, AI's reach is widespread. It is not just the technological proficiency that is at stake, it is also the manner in which these tools shape human interactions, institutional operations, and societal norms. The proliferation of AI technologies prompts critical consideration of ethical frameworks and accountability standards necessary to navigate the future. The societal impacts of AI raise practical, legal, and moral questions that demand thoughtful examination and proactive management. AI technology's influence on the job market illustrates one of its most conspicuous societal impacts. Automation and AI tools can enhance productivity and reduce costs, but they also risk displacing workers whose jobs can be automated. While some roles become obsolete, new job categories emerge, necessitating the reskilling and upskilling of the workforce. This workplace transformation sparks debates on the right balance between technological advancement and employment security. It underscores the need for policies that support workforce transitions and foster an environment where humans and AI can coexist productively. Concerns regarding income inequality and employment gaps amongst different socioeconomic groups are amplified in discussions around AI-induced automation. Concurrently, AI and machine learning have revamped the landscape of information accessibility and media consumption. Algorithms personalize user experiences on digital platforms, tailoring content to individual preferences and behaviors. While this customization can streamline information retrieval and enhance enjoyment, it can also create echo chambers, reinforce biases, and diminish exposure to diverse perspectives. Algorithms lack the human capacity for nuanced judgment and may inadvertently promote misleading or harmful content with no intent or understanding of consequence. Society must grapple with the ethical consequences of these automated content management systems, ensuring they do not contribute to misinformation or social polarization. Data privacy and security are paramount when considering the ethical implications of AI. The vast amounts of data required to train machine learning models raise concerns about who has access to this data, how it is used, and how it is protected. As AI systems become more adept at processing personal information, the potential for misuse grows. Ethical AI deployment demands strict protocols for data handling, transparency about data use, and robust security measures to protect against breaches. The obligation to safeguard user privacy intersects with the technological imperative to refine AI models, creating a tension between innovation and individual rights that must be navigated with care. The impact of AI on the legal system and governance also merits attention. AI can expedite legal procedures through predictive analytics and document automation, but it also presents challenges in ensuring fair and impartial justice. The deployment of AI in law enforcement, such as for predictive policing, carries the risk of entrenching existing prejudices if the underlying data reflects historical biases. The legal frameworks in place may not adequately address the novel situations created by AI, necessitating updates and revisions to maintain rule of law and protect individual freedoms. Governance structures must evolve to incorporate oversight of AI systems, ensuring they align with societal values and legal standards. Bias and discrimination in AI present complex challenges. Since machine learning models learn from historical data, they can perpetuate and amplify existing societal biases. Biased algorithms can result in discriminatory outcomes, affecting marginalized groups disproportionately. It is crucial to develop measures that detect and correct for biases in AI systems. Audit trails, diverse datasets, and inclusive design practices are vital to create equitable AI outcomes. The ethical mandate is to foster AI that contributes positively to society without exacerbating social inequities. The integration of AI into healthcare epitomizes both the promise and peril of these technologies. AI has the potential to revolutionize medical diagnostics, personalize treatments, and streamline healthcare administration. However, it also raises ethical questions regarding the opacity of decision-making processes and the potential for algorithmic errors in high-stakes medical scenarios. Questions of liability, consent, and patient autonomy in the context of AI-assisted healthcare are at the forefront of ethical debates. Ensuring that AI in healthcare serves the well-being of patients and maintains the trust of the public is imperative. AI's impact on education opens avenues for personalized learning and access to information, but carries concerns about the reinforcement of educational disparities. Adaptive learning systems can provide students with individualized instruction, addressing unique learning styles and pacing. However, discrepancies in the availability of technology and quality of datasets could widen the educational gap, between different socioeconomic groups. Ensuring equitable access to AI educational tools and addressing the potential for bias in educational content are necessary considerations as AI becomes further incorporated into educational systems. Consumer markets are increasingly influenced by AI in terms of both product development and consumer interaction. Recommendation engines personalize shopping experiences, while AI-driven analysis informs product design. Nevertheless, there are ethical concerns regarding consumer manipulation, consent, and privacy. The use of AI to influence consumer behavior must be scrutinized for potential exploitation or unethical practices. Transparent, fair, and privacy-preserving systems are essential in maintaining consumer trust in an AI-driven market. International relations and security issues are also entwined with the development of AI. The potential for AI to be used in surveillance, cyberattacks, or even autonomous weaponry raises significant ethical and safety concerns. The international community must debate and establish norms and agreements on the responsible use of AI in security and defense. The implications for global stability, war prevention, and ethical conduct in conflicts are profound and necessitate careful consideration and regulation. As AI continues to develop and integrate into various aspects of society, the need for ongoing ethical review and adaptive policy becomes clear. AI technologies do not exist in a vacuum. They are products of human design and operate within human societies. Their development and implementation must be steered by thoughtful consideration of the potential impacts on individuals and communities. Addressing the ethical considerations of AI requires multidisciplinary collaboration, involving ethicists, technologists, policymakers, and the public. Our collective responsibility is to steward the development of AI in a way that maximizes its societal benefits while mitigating potential harms. The path forward is not solely about harnessing the power of AI, but about ensuring it aligns with fundamental human values and the greater good. 1.7 AI in various industries. Artificial intelligence, AI, has woven itself into the fabric of various industries, transforming the way businesses operate by driving efficiency, enhancing customer experiences, and creating new opportunities. The agriculture sector, which historically depended on the experience and intuition of farmers, is beginning to adopt AI to optimize production. Data-driven farming through AI applications allows for the precise calculation of watering schedules, soil health, and crop health through image recognition and predictive analytics. Moreover, AI-driven drones and robots can perform tasks such as planting seeds, fertilizing crops, and harvesting at a scale unattainable by human labor alone. In the healthcare industry, AI is playing a pivotal role in diagnostic procedures, personalized medicine, and patient care. Machine learning algorithms can analyze medical images such as X-rays, MRIs, and CT scans with a level of precision that often surpasses human radiologists. Furthermore, AI systems are being trained to detect disease patterns and predict patient outcomes from vast datasets. Personalized treatment plans generated using AI are tailored to the individual patient's genetics, lifestyle, and environment, which considerably improves the efficacy of interventions. The financial sector has also embraced AI for various applications, from fraud detection to customer service and algorithmic trading. Financial institutions leverage machine learning models to identify patterns of fraudulent activity and prevent them in real time, saving millions in potential losses. Customer service has been revolutionized by AI-powered chatbots capable of handling a multitude of inquiries simultaneously, providing swift and accurate responses. In trading, AI algorithms analyze market data to predict stock price movements, allowing for trades that can be executed far more swiftly than would be possible by human traders. Retail industries have found AI invaluable for both customer-facing and behind-the-scenes operations. AI helps in analyzing customer data to personalize shopping experiences, recommend products, and manage inventories. For example, predictive analytics can forecast product demand, thus streamlining supply chain and stock management. Additionally, virtual assistants and chatbots provide personalized customer assistance, increasing engagement and improving customer satisfaction. In transportation and logistics, AI is instrumental in route optimization, autonomous vehicles, and predictive maintenance. AI-driven analytics enable transportation and logistics companies to optimize their routes, thus reducing fuel costs and delivery times. Autonomous vehicles, guided by AI, promise a future with enhanced safety and efficiency on the roads. Predictive maintenance, another AI application, uses sensors and data analytics to preemptively identify potential mechanical issues, thereby reducing the likelihood of breakdowns and increasing the longevity of vehicles. The entertainment industry is tapping into AI for content personalization, which drastically alters how people consume media. Streaming services like Netflix and Spotify use AI algorithms to analyze viewing and listening habits, suggesting content that keeps users engaged. This AI-driven personalization has set a new standard for content delivery, creating an expectation among consumers for services that understand and cater to their individual preferences. In the field of education, AI is transforming the learning experience with customized educational paths and virtual tutoring. AI systems consider a learner's pace, style, and understanding, offering personalized lessons that are more effective than traditional one-size-fits-all approaches. These systems can also provide immediate feedback, track progress, and identify areas that require additional attention, offering a more supportive educational framework for students. Manufacturing industries are utilizing AI to automate processes, conduct quality control, and manage supply chains. AI-powered robots can complete tasks such as assembly and packaging with high precision and speed, maximizing production rates. AI systems in quality control detect defects or deviations more accurately than human workers, ensuring the consistency of manufactured products. Moreover, AI in supply chain management forecasts demands and optimizes inventory, which minimizes overproduction and waste. In the field of cybersecurity, AI is essential for defending against sophisticated threats. AI systems monitor network activity to identify unusual patterns that may signify a breach, responding in real time to mitigate risks. These systems adapt and learn from each attempted attack, becoming more robust in their defense mechanisms over time. Energy sector companies are implementing AI to enhance efficiency and facilitate the move towards renewable sources. AI can manage and distribute energy resources more effectively, integrating fluctuating supply from renewables such as solar and wind with demand. Smart grid technology, empowered by AI, adjusts the flow of electricity to where it's needed most, reducing waste and optimizing the use of sustainable energy sources. Across these diverse verticals, the integration of AI has necessitated a fundamental reassessment of work roles, business models, and competitive strategies. Some businesses have experienced disruption, needing to adjust to the new AI-driven paradigm quickly or face obsolescence. Others have embraced AI as part of their growth strategy, witnessing enhanced productivity and innovation. Companies adopting AI technologies are finding that these tools not only optimize existing processes, but also enable the creation of entirely new products and services. This has established AI as a critical driver of the fourth industrial revolution, characterizing the current wave of digital transformation in the global economy. 1.8 Future Trends and Predictions in AI. As we consider the future of artificial intelligence, AI, and machine learning, it is clear that these technologies will continue to evolve at an exponential rate. The advancement of AI capabilities has been relentless, and predictions about where AI is headed often seem as fantastical as they are logical. Developments in machine learning algorithms, data processing capabilities, and computational power are fueling innovation across every sector of the economy, from healthcare to finance, and from automotive to entertainment. Reflecting on current trends, we can anticipate a number of future directions for AI. One of the notable trends is the move towards more general AI systems, which exhibit a broader understanding and can perform tasks across different domains. Current AI systems excel at specific tasks, but the aim is to create more adaptable algorithms, ones that can learn and apply their intelligence much like a human can switch from one task to another with relative ease. This quest for general AI, or artificial general intelligence, AGI, is a holy grail for researchers, which promises enormous potential but also poses significant technical challenges and ethical considerations. Advancements in AI interpretability and explainability will become crucial as AI systems become more prevalent and make decisions in critical areas such as medicine, law enforcement, and autonomous driving. There is a growing need for AI systems to be able to explain their decisions and thought processes to users. This trend is not only driven by the need for public trust, but also by regulatory considerations. As data protection laws become stringent, the ability for an AI to elucidate its decision-making process will be vital for compliance and to ensure that AI-driven decisions are fair and do not discriminate against certain groups. The integration of AI with other disruptive technologies is a trend we will see more of in the coming years. Technologies such as blockchain, IoT, Internet of Things, and edge computing are converging with AI to generate new insights and efficiencies. For example, AI is used in conjunction with IoT to optimize manufacturing processes through predictive maintenance of machinery. Similarly, by using blockchain, AI systems could make decisions that are not just smarter but also more secure and transparent. These integrations will result in multifaceted platforms that can leverage the strengths of each technology, leading to innovative solutions for complex problems. Another potential trend is the democratization of AI, as tools and platforms become more user-friendly and accessible to a wider range of people, regardless of their technical expertise. This is spurred by the proliferation of cloud-based AI services offered by major tech companies, which reduce the barrier to entry for developing and deploying AI solutions. Democratization is likely to spur a new wave of creativity and innovation, as non-experts contribute fresh perspectives to the development of AI applications. The rise of ethical AI is another significant trend that will shape the future of this field. As society begins to understand the implications of AI, there is increased focus on developing AI in an ethical manner. This involves creating algorithms that do not inherit biases from their human creators or the data they are trained on. Ensuring ethical AI implementation requires diligence in the design, development, and deployment stages, along with continuous monitoring to prevent unintended consequences of AI applications. In terms of applications, personalized AI has the potential to revolutionize consumer experiences. AI systems will become more adept at understanding individual preferences and behaviors, enabling personalized recommendations and services. This can manifest in bespoke content delivery, personalized healthcare regimens, and even individualized learning plans in education. The extensive data these personalized AIs will collect can further contribute to their accuracy and utility, though it will also raise valid concerns about privacy and data security. Augmented intelligence represents a paradigm where AI enhances human decision-making rather than replaces it. This collaborative approach between humans and machines can lead to more effective outcomes than either could achieve alone. For example, augmented intelligence is already proving beneficial in healthcare, where AI systems provide doctors with recommendations based on vast datasets that can aid in diagnosis and treatment plans. This trend acknowledges the irreplaceable value of human intuition and experience while leveraging the brute computational power of AI. The push toward autonomous systems is another clear trend. These systems will likely become more capable and more common, handling complex tasks without human oversight. This can lead to advances in autonomous transportation, with self-driving vehicles potentially becoming ordinary fixtures in urban landscapes. Similarly, drones and autonomous robots could undertake tasks like delivery services, agricultural monitoring, and even complex construction projects. Machine learning algorithms are becoming increasingly efficient, enabling them to run on devices with lower computational power. This trend, known as edge AI, allows for real-time processing and decision-making on local devices without needing constant connection to the cloud. Edge AI can enhance privacy and reduce latency, making it ideal for applications where immediate responses are crucial, such as in autonomous vehicles or mobile applications. Finally, the employment landscape in the age of AI will undergo transformation, as AI and automation continue to reshape the types of jobs available and the skills required to perform them. There will be increased demand for AI literacy across all sectors, and a shift in focus toward roles that design, develop, maintain, and regulate AI systems. Despite fears of job displacement, history has shown that technology innovation can create new industries and employment opportunities, though it may simultaneously render others obsolete. Predicting the future of AI and machine learning is not an exact science, given the rapid pace of technological change. What is certain is that AI will permeate more aspects of our lives, posing unique challenges and offering unprecedented opportunities. As we advance, it is crucial that the development of AI remains aligned with societal needs and ethical standards, ensuring that these powerful tools benefit humanity as a whole. 1.9 Challenges in AI Development. Artificial intelligence, AI, and machine learning represent revolutionary approaches to solving problems that have historically required human cognitive abilities. In its development, AI has moved from simple rule-based systems to complex networks capable of deep learning and autonomous decision-making. Machine learning, a subset of AI, entails training algorithms on data to make predictions or decisions without being explicitly programmed for the tasks. Despite the remarkable advancements and potential applications, the pathway to creating effective AI systems is fraught with a multitude of challenges. Addressing these challenges is essential for the sustainable progression of AI technologies. One significant challenge in AI development is the procurement of quality data. AI and machine learning models require large volumes of data for training. However, the accessibility of such data can be limited, and when available, it often presents issues like imbalances, noise, and biases. Quality data must be representative, relevant, and sufficiently voluminous to avoid overfitting where a model learns the training data too well, but fails to generalize to new data. Additionally, data might be subjected to privacy constraints and regulations like the General Data Protection Regulation, GDPR, making the collection process more complex and legally sensitive. Another critical challenge is algorithmic complexity and the selection of appropriate model architectures. The design of the models must resonate with the complexity of the problem at hand. Simple problems might require straightforward algorithms, while more intricate ones necessitate complex neural networks such as deep learning. However, these require substantial computational resources and expertise in tuning numerous parameters. Moreover, deep learning models, often referred to as black boxes, pose interpretability issues. Understanding how they make decisions is not always straightforward, which raises concerns in decision-critical domains such as healthcare and law enforcement. Computational costs and resource demands are also substantial hurdles to AI development. Training robust machine learning models typically needs considerable computational power and often specialized hardware like GPUs or TPUs. These resources can be expensive and contribute to high operational costs. In addition, with the increasing size of datasets and complexity of models, energy consumption becomes a pressing issue, prompting a need for sustainable and energy-efficient AI solutions. This not only affects operational costs, but also has broader implications for the environment and society. The maturation of AI systems must also wrestle with the scarcity of skilled professionals. Although interest in AI and machine learning is at an all-time high, the field is still relatively new, and academic programs are struggling to keep pace with the industry's advancement. There is a significant gap between available qualified individuals and the number of experts needed, creating a bottleneck in innovation and deployment. This talents gap can slow down AI research and development, making it difficult for organizations to implement AI solutions effectively. AI and machine learning evolution is paralleled by ethical concerns and the need for responsible AI. As AI systems become more integrated into daily activities, the impact of decisions made by these machines becomes increasingly substantial. Issues of fairness, accountability, and transparency come to the fore. AI systems are prone to replicating and even exacerbating existing biases present in their training data, leading to unfair outcomes. It's imperative that developers build AI with ethical considerations at the core, ensuring that these systems do not perpetuate inequality and are developed with the ability to explain their reasoning. The sensitivity of AI systems to adversarial attacks poses further challenges. There exist vulnerabilities in many AI models that can be exploited by feeding them intentionally perturbed data, which can lead to incorrect outcomes. As AI systems are increasingly deployed in security-sensitive areas, the potential for such adversarial attacks becomes a serious risk that must be mitigated. Developing more robust algorithms that can withstand these attacks is a priority, but it remains arduous work entailing much research and testing. Furthermore, machine learning models frequently face the issue of scalability. Many AI systems are developed and trained in controlled environments with limited datasets. Upon deployment in real-world applications, these models are exposed to a dynamic and often unpredictable influx of data. This shift can lead to a degradation of the model's performance over time or when applied at scale. Managing this transition and ensuring that AI systems can scale effectively without a significant drop-off in reliability is a critical task in AI development. Interdisciplinary collaboration poses yet another layer of complexity. AI development often requires expertise from a variety of fields, including computer science, mathematics, statistics, cognitive science, and domain-specific knowledge. Orchestrating these discrete sets of expertise towards the common goal of building a functioning AI system can be intricate. It demands a collaborative infrastructure that is not always present in organizations, along with communication strategies that effectively bridge the gap between different domains of knowledge. Lastly, as AI becomes more widespread, the legal and regulatory landscape surrounding its implementation evolves. Governing bodies worldwide are attempting to keep pace with technological advances by crafting legislation that protects consumers and addresses the various implications of AI deployment. Compliance with these evolving regulations can be onerous for developers, as it may require periodic modifications to the algorithms or the way data is handled. Keeping abreast of regulatory requirements and ensuring that AI systems comply without stifling innovation is a constant balancing act. AI and machine learning have the potential to significantly alter every aspect of modern life. Despite the extraordinary progress made, the development of AI systems comes with a suite of formidable challenges that need careful navigation. From the limitations of data and computational resources to ethical considerations and regulatory compliance, developers must diligently address each aspect to propel AI forward responsibly. The advancement of this technology depends not only on technical breakthroughs, but also on tackling these multifaceted challenges, which demand a concerted effort from diverse stakeholders in the AI ecosystem. This hard work and dedication are essential for ensuring that AI technology can continue to evolve in a way that serves humanity beneficially, responsibly, and sustainably. 1.10 Case Studies, AI Success Stories. Artificial intelligence, AI, and machine learning, ML, have transformed myriad industries, yielding powerful solutions to complex problems and improvements over traditional methods. To fully grasp their impact, we will examine several case studies where AI and ML not only succeeded but surpassed expectations, setting new standards for technology applications. The first case of AI's impact is seen in healthcare, where algorithms refine diagnoses and treatment plans. A prominent example is IBM's Watson for Health. Watson's ability to analyze the meaning and context of structured and unstructured data has empowered it to aid in the treatment of diseases such as cancer. By ingesting millions of pages of medical literature and patient records, it provides personalized treatment recommendations with a high degree of precision. Studies have showcased Watson's potential to dramatically change the treatment landscape by identifying relevant treatment options that align with the latest research. In finance, AI and ML are revolutionizing the industry by detecting fraudulent transactions with unparalleled speed and accuracy. Systems like MasterCard's Decision Intelligence use sophisticated algorithms to analyze transaction data in real time, identifying patterns indicative of fraud. By examining thousands of data points, from transaction size to merchant location, AI models have significantly reduced false declines while catching fraud attempts that may have eluded traditional systems. This allows financial institutions to save billions annually while also improving customer satisfaction. In the realm of transportation, AI has enabled the emergence of self-driving cars, epitomized by the advancements made by companies like Tesla and Waymo. Through deep learning techniques, these vehicles process data from various sensors to navigate and respond to dynamic road conditions. The data, collected over millions of miles of driving, improves the system's driving algorithms over time. While full autonomy hasn't yet been reached, the progress illustrates AI's potential to reduce accidents, improve traffic conditions, and reinvent transportation. Customer service has benefited from AI through the proliferation of chatbots and virtual assistants. For instance, the AI-driven chatbot implemented by Sephora has transformed the shopping experience. By understanding customer queries through natural language processing, the chatbot provides personalized recommendations, makeup tutorials, and appointment booking services. This interactive platform not only improves customer engagement, but also streamlines operations and increases sales. In the field of agriculture, AI plays a pivotal role in precision farming. Companies like John Deere use machine learning to analyze satellite imagery and sensor data to monitor crop health and soil conditions. These insights enable farmers to optimize irrigation, fertilizer use, and harvesting strategies. As a result, farms can boost yields, reduce waste, and minimize environmental impacts. Such granular control over agricultural practices demonstrates the vast potential of AI in resource management. AI success extends to the field of entertainment as well, with platforms like Netflix using recommendation algorithms. By analyzing viewing habits, reviews, and even pause and rewatch patterns, Netflix personalizes the user experience, suggesting content that keeps subscribers engaged. Such tailored experiences not only improve customer satisfaction, but also contribute to increased retention rates and time spent on the platform, ultimately boosting revenue through precise content curation. In the environmental sector, AI assists in climate modeling and the monitoring of biodiversity. For example, Microsoft's AI for Earth program allocates resources and services to researchers and organizations working on environmental challenges. By using AI to analyze large datasets, such as those from climate simulations or wildlife surveys, patterns and solutions can be identified more quickly and accurately than ever before. This has crucial implications for conservation efforts, policy making, and the fight against climate change. The retail industry has seen a revolution with the implementation of AI in inventory management and customer insights analysis. Walmart, one of the largest retailers, employs AI algorithms to predict stock levels and optimize supply chain management. Through machine learning, Walmart efficiently anticipates demand, reduces overstock, and avoids understocking, which has led to better inventory turnover ratios and reduced operational costs. In the world of manufacturing, AI-driven predictive maintenance has become a game changer. By using sensors and IoT devices, manufacturing equipment collects data points which are analyzed by AI to predict potential failures before they occur. German conglomerate Siemens uses such AI systems to ensure the smooth operation of turbines and other heavy machinery. This preemptive approach minimizes downtime and extends the life of equipment, bringing considerable cost savings and efficiency gains. Lastly, in academia, AI tools have enabled breakthroughs in research by optimizing data analysis and facilitating the discovery of new insights. Google's AI subsidiary DeepMind created AlphaFold, an AI system that predicts protein structures with astounding accuracy. This breakthrough has massive implications for biological research and drug development, with the potential to accelerate the discovery of treatments for diseases that have long eluded scientists. DeepMind's success with AlphaFold illustrates the transformative power of AI in pushing the frontiers of human knowledge. These case studies are a mere snapshot of the successes achieved through AI and ML across various domains. They exemplify the transformative nature of these technologies, underscoring their potential as powerful tools in addressing complex challenges. As we continue to embrace AI and ML in various sectors, we can anticipate further innovative solutions and improvements in efficiency, contributing to significant advancements in both the professional and personal realms.